So I'm going to talk today about FastRoute. It's a scalable load-aware Anycast routing architecture for modern CDNs. It's something that we've had in production for the last 2 years or so, and it's handling traffic for a number of Microsoft's online services. So, as I mentioned just a second ago, Microsoft's online services exist in a small set of data centers distributed throughout the world. We can't have our services in a significant amount of locations. You can't have Bing running in hundreds of locations. It's just too expensive to do. So we have Bing and Outlook and other highly compute-intensive applications running in a small set of data centers. Then what we do is we put edge nodes close to users, and that helps reduce the network latency of such services. Essentially exactly the same as what the last talk was saying is an important part of page load time. So what I'm going to present today is FastRoute, and this is a fully distributed mechanism to direct users to a nearby edge. An important part of that is that this is a system that handles global traffic with no global information at all. And that's an important characteristic of this particular solution. So why use an edge? So here's an example. I've used Bing as an example here. So Bing might exist in a data center near Microsoft's headquarters in Seattle, for example. And then we've got a user, which happens to sit in Australia here, a vital user from my perspective. Actually, this is even more important given what's happening this weekend. And one of the most important users of Bing and Microsoft services is my mum. And she's probably the first person to complain if it's not working as she'd expect. So my goal is to make Bing or other web pages faster for my mum. That's what I'm trying to do here. So let's look at what the round trip time or latency for my mum to get to Bing data centers in Seattle. So if you look at the round trip time for my mum to get to Seattle is about 180 milliseconds. So in order to get the first byte of Bing's web page, or the search results, there is at least a network latency of 2 times the round trip time for the TCP session to be established and get the first byte, which is about 360 milliseconds. 360 milliseconds is a lot of time, especially when you're considering that we want to deliver search results in around the 1 second mark. So it's a big number. So what we do is we put edge nodes close. So here as an example, I put an edge node in Sydney as an example here. And between my mum and this edge server, it's very low latency, so it's 20 milliseconds. And then that edge server to get back to Bing's data center is about 170 milliseconds here. So when we look at the latency of what this request actually experiences here, is you have the TCP startup time for my mum to connect to the edge server, which is 2 times what I'd say is a short round trip time, so 2 times 20 milliseconds, plus 1 times the long round trip time, because that TCP session is multiplexed over many users and you don't have to establish that connection. So what you get is a latency of about 210 milliseconds at this point. So remember it was 360 last time and now 210 with the use of this proxy. So this is, saving of 150 milliseconds. So this is my Mother's Day present to my mum. I've made Bing 150 milliseconds faster for her. So now we have all these edges around the world, and I'm sure everyone here has a mum and they'd like to make the Bing's page load time faster for their mum. So how do I pick which edge to direct users to? And once I've picked which edge to send them to, how do I do it? What's the mechanism I use to redirect those users to the right location where I'd like to send them? So here is the traditional approach, and this is used by a number of companies around the world, and this is the map the internet approach. And here is where I've got 4 edge nodes as an example here, and users spread throughout the world. And now we want to get those users to connect to a nearby edge location. So first thing you need a map calculator. An example of this was Conviva's talk yesterday. You collect a huge amount of performance data, you analyze it, and you figure out the best place for this user is this particular location. And then what happens is you push that into a DNS service. And that's the most common way to do this. It's a very transparent way for users who you don't have control over the clients to direct them to the location you'd like to go. So now users make DNS requests, it hits our DNS server. The DNS server then responds back with different IP addresses based on where it thinks the best location is to serve those, and the users then connect to their closest location. If a failure occurs, then the map calculator has to detect this, process it, figure out what the next best location is, push that to the DNS server, the DNS TTL has to then expire, and then users will be routed to the next closest location. So here, the users in Australia might be routed to Edge in Singapore, for example. So the primary benefit of this approach is that you have a significant amount of control. You can direct any DNS request to any node of your choosing. And it's a very fun problem to solve, like Conviva had the talk yesterday. It's a fun thing to figure out where should I actually send users to. There is a trade-off though, and that is there is a high operational cost and complexity of building that system, which actually collects all the information, processes it, and figures it out. Also, DNS routing, you're getting the DNS request to direct users to the location of your choosing. That can be inaccurate at times, and sometimes you're sending users to not the place you'd actually really like them to go to. And one of the big things about the operational cost here is that if you make it too complex, the set of people which can operate that system and the people who get called in the middle of the night reduces. And if it's too complex, you are the only one which gets called when there's a problem in the middle of the night. So the goal here was not to get called up in the middle of the night. There is an alternative, though, to this particular approach, and that's an Anycast-based approach. Here we have every edge location having exactly the same IP address. Each edge then announces into BGP the same prefix, and then you let BGP's routing protocols choose which is the closest point for each particular user. So in this case, the DNS server gets the request from all users, and you return A back to every single user, and then the users connect to A. It was interesting when we switched this on to start with. It was how good is this going to be? You don't know where users are actually going to route to. An example I have of this, it was actually quite good for Microsoft's network at least, where in Europe, when we switched this on, only 2 ISPs in Europe didn't route to a location inside of Europe. So our peering inside of Europe was actually good enough that we only had to go and get 2 ISPs to get additional peering to get the connection to connect locally inside Europe. An important thing about this to notice is that there is no centralized controller. We don't have that map controller. We don't need it, this particular approach. We don't need to figure out where to send users. You relinquish control and you let the internet handle where to send users. When a failure occurs, the users in Australia here, their edge fails. All that happens is that edge then withdraws its BGP route and users are then rerouted to the next closest location. So the users go to Singapore. The benefits of this is it's really, really simple. The only thing you need to do is build software inside of an edge node which determines whether it's healthy or not. If it's healthy, it announces the BGP route. If it's unhealthy, it withdraws the BGP route. And you're not reliant on DNS-based proximity routing to choose where you're actually sending users. There is a trade-off though, and this is that we're relinquishing control to the internet of where to actually direct users to. So in the case of the Europe example I gave before, maybe with a DNS-based approach, those ISPs which we were sending to the States could have been rerouted to Europe and got better performance. But we're saying, internet, you handle that, we trust you. The other part of this is that you have no control over the load landing on any individual node. If one ISP changes its decision of where to route traffic, whoosh, all the traffic goes and then bombards one edge, and you hit an overloaded node situation, and then you've got to figure out, what do I do with that? How do I handle that particular load? And that's what we'll talk a little bit more about today, how we've done it. So what we'd like to have in FastRoute's design is we want it to be very simple and very easy to operate. We want it to be highly available, so we want to react to failures. And we want it to be high performance. And in high performance here, it doesn't have to be an Oracle and the best that it could possibly be. It had to be better than the existing solution which we had, a third-party CDN. So what we'd like to have is a solution with the simplicity of Anycast, but with just enough control to handle overloaded nodes. We're willing to sacrifice some performance in order to handle this particular situation. We don't exactly need 100% control over where we're directing traffic to. We just need enough to handle the overloaded node situation. So there's 2 questions which come out of this. Firstly, does Anycast provide sufficient performance? And 2, how can we manage the rare but expected individual overloaded node situation without sacrificing Anycast simplicity? And I'm calling it rare here because one thing when we're building out edge node locations is that the incremental cost of adding more machines or more capacity to them is relatively low compared to actually putting the machine or the edge node out there. So we can over-provision these enough such that load is relatively rare. So the first question, the performance of Anycast, what did it look like? And this is a picture, it's slightly, had to try and modify it to make it okay to publish outside of Microsoft. So this is trying to show the performance gains which we got when we moved to an Anycast-based solution over our third-party CDN which we were using before. So in this picture, I saw everyone else yesterday saying what was good, so I took a leaf out of that book and said anything above 0% here in this case is good. We've got the 75th percentile and 95th percentile. So you can see for ISP 4 here, which is, these are the 10 major ISPs in the States by, 10 major ISPs. This particular ISP got a 15% performance gain by using Anycast versus using the Unicast-based third-party CDN, which we were comparing against. So performance of Anycast wasn't a problem for us. This was a great piece of information to justify moving to the next step and not building a large-scale map controller solution. One thing now, if we talk about how to manage the load, I wanted to talk about what do these nodes actually look like? What is an edge node? So an edge node consists of a bunch of machines, essentially, but the number of machines in each edge location is different. So if we have an edge node which exists inside of an ISP, for example, then that might be not many machines at that particular point in time. And it's harder to add more machines because we don't have control over the facility. So if a machine fails, we can't replace it as easily. Then we have, that's the green ones in here. We might have those spread throughout the whole world. Then we've got backbone nodes, which might be at the edge of the Microsoft network. And these are well distributed. Microsoft's got a global network, so this is fairly well distributed. And these nodes have more capacity, but not infinite amount of capacity to handle load. And they're reasonably close to users, but not as close as what an ISP node would actually be. Then we have edge nodes which actually exist inside of our data centers. So you can think of these as existing inside of Azure as an example, where you have essentially infinite amount of capacity to handle whatever load you throw at it. And these are in fewer locations which will be further away from users though. So how do we take advantage of these? Well, we're going to use what we're going to term layers of Anycast addresses. So here we've got 3 different Anycast addresses. The first one is IP address A. IP address A, every single edge node, no matter where it is, announces that particular IP address. The second IP address is IP address B, which consists of only the backbone and data center nodes. And IP address C is just a data center node. So it's like a Russian doll type thing set up of these particular IP addresses. So now how do we use these 3 different Anycast IP addresses to handle the load on the edge network? So here's a picture. I've shown it the green, yellow and red, same type of thing with the edge, backbone and data center nodes. So now here we have users landing on one particular edge node. That edge node is now hot, whatever hot means, it's loaded. So now we want to remove the load constraint on this particular node. So what we do is we throw traffic to the next layer. We don't care where it goes, we just say, okay, I'm hot, I will throw it to the next layer. And that layer can handle it. I don't care what node, just handle it. This was an architecture choice not to try and send traffic to a node in the same layer. And the reason is, if you start sending traffic from one node in a layer to another node, and then that node gets overloaded, then it starts throwing traffic back. You've got an oscillation problem which you have to solve. We chose not to solve it and just make sure there are no loops and just funnel the traffic up until you hit the data centers. So yeah, as I mentioned, the next layer does exactly the same thing. If a request lands on an edge in the second layer, it's hot, it throws the traffic over the wall, lands in the data center, and a data center is provisioned to actually handle that. And as I said, the last layer has what you can assume is infinite capacity to be able to handle whatever load you throw at it. So how do we throw this traffic at this point? So the first thing that we do is we co-locate all of our DNS servers with our HTTP proxies in every single location. And then we configure our IP addresses for our DNS servers in exactly the same layered approach. So we have the 3 different sets of IP addresses. Then the DNS server co-located with the HTTP proxy monitors the load on itself and determines whether it's getting loaded or not. and then probabilistically starts returning a CNAME or a DNS redirection to the next layer. And the next layer does exactly the same thing. It's recursive. You can have as many layers as you want here, or as long as there are no loops in the redirection, you can set this up in whatever way you'd like. So an important part of this is that it preserves the independence of each node. There is no real-time communication outside of an individual node. So we're managing global traffic without having global information. And that was a very important artifact of this particular solution. There is a major assumption, though, when we're doing this, and that is that a DNS request for a user lands in the same location as the HTTP request, i.e. the requests are self-correlated. This is not actually guaranteed for all particular requests. An example of this is if you're in Comcast in Seattle, your DNS server in Comcast is either in Salt Lake City or in Portland. So if we have edges in Portland and in Salt Lake City, the user, myself who's sitting in Seattle, would hit the HTTP request would land in Seattle, but my DNS request would land in Salt Lake City or Portland. So it's not particularly guaranteed. It's not guaranteed. But is it good enough to handle the overloaded node situation? Well, this is what it looks like in practice. This is a picture. I don't expect you to try and understand this picture exactly. I'll give you some key concepts out of it. The ideal 100% self-correlated line is on the right-hand side there. That's what, if every node was 100% correlated, it looks like that. What it looks like in practice is that amazingly straight line up until about 50% and then tails off. What this means is that more than 90% of nodes have more than 50% self-correlation. What this means is that each node can handle, if you're 50% correlated, it means that you can handle 200% of your provision capacity when you're with this particular mechanism. So you can throw 50% of your traffic to the next layer. So what does this look like in practice? Like this is running. Like this is what our algorithm looks like. We set an overload threshold for a particular resource. We say, okay, Bing, define what your overload metric is, and then we're going to monitor that, and we're going to try and keep that metric below a particular level, and we're going to offload traffic to keep that below. So here the traffic spikes up in the top graph, and then you see at the bottom point, we start offloading more and more, and then once we've offloaded too much, we bring the traffic back, and then we try and keep it under this particular level. It's not exactly a complicated algorithm. It's just if you're overloaded, increase the rate of offloading. If you're underloaded, decrease. That's pretty much it, and it makes it a very simple solution. So in summary of what we've actually got here, or what we built, is we statically configure edges in multiple Anycast layers. Each edge independently monitors its own load and decides whether I'm going to throw the traffic to the next layer or keep it on my own local Anycast IP address. And the final layer is dimensioned sufficiently to handle all load that you can possibly throw at it. The important part here is that edge nodes act independently without any knowledge outside of a particular edge, which means that edges can go up and down. No other edge needs to know about it. We can add new edges in new locations, and nothing needs to be updated in a central repository to say this is a new edge and this is available. So it makes it a very operational system at that particular point. So at that point, I'll end it and I'll take any questions which people have. Thank you very much. Yes.
Hey, this is Matt Welsh at Google. This is very interesting, and actually I'm interested because I used to work on our version of this, which actually uses the map the internet approach. Not exactly that, but something close. I was curious to know how you deal with the case where you have multiple nodes in the same geographic area. So for example, if I had multiple nodes in the same ISP, in the way you described it, it sounds like you'll always fall back from the edge node back to something closer to your core data centers rather than falling over across those. Is that true? Yes.
So there was a choice to not try and move traffic across. Theoretically, if we wanted to add a bit more complexity, we could figure out which of those nodes is most loaded most of the time and configure another layer so one node throws to the next. And as long as there's no cycles in the layers, you can keep throwing the traffic. So we could do it that particular way. So
and then quick follow-up. So in my understanding is that your measurement of load is based on the DNS query load, not the actual QPS on the service?
No, so the DNS server itself just asks the proxy service,
I see.
like, what is your load? And we specifically didn't want to know what
Got
load
it.
was. Just give us a number between 0 and 100, and we will use that as our metric to move traffic.
Great, thank you.
Thank you.
Kostin Reicher from Polytechnic Bucharest. So really cool work. I was wondering, perhaps I just didn't get it from the talk.
Yep.
So you mentioned that you're using Anycast to actually connect via
Yes.
HTTP. I mean, Anycast is supposed to be fickle with routing and
Yep.
everything, and your TCP connection
Yep.
will break. So, I mean, that's what we academics think.
Yep.
So how is it in practice?
So it's funny, that's the exact question which I get almost every time when I present this. I try to avoid it, but what we found is that, well, when we were going with this, is that there are a number of other CDNs which used Anycast. And we're like, okay, it works for them. I think it's going to be okay, and it's not going to break the internet. We did our own experiment as well, so we used Gomez and user agents in this particular graph, and we looked at the availability of our Anycast destination of our third-party CDN, which was Unicast-based, and our own. And it was about the same over the whole period of time. We also ran an experiment with Bing users to download a small file and report how many failures, I guess, they got before we moved over. And we didn't see any noticeable issue, I guess, with TCP sessions being broken.
I mean, since you're doing DNS Anycast anyway,
Yep.
why would you use Anycast for the addresses of the proxies themselves? I mean, you could actually use...
Yep, so one approach is that we could use DNS Anycast and then return the unicast of the edge itself. And at that point, this mechanism would work exactly the same. Your correlation would be 100% at that point in time. The reason we didn't go that direction is for performance reasons. We wanted to get users to the closest particular location without having to worry about where their DNS server was located.
Thanks.
Yes.
Hi, I'm Edward from Cornell, and just a quick follow-up on that earlier question. You have this idea that the inner ring nodes are closer and closer to your data center and higher capacity.
Yep.
So when you have a failover because of the edge node being overloaded,
Yep.
there's a corresponding decrease in performance because users experience longer latency.
Yep.
How sharp is that degradation as outer nodes fail?
So we didn't look at it specifically because we expect this situation to be rare, and if we hit an overloaded node, then performance isn't our number one priority at that point. It is serve the traffic reasonably close. And with the Microsoft's network being as distributed as it is, like falling back to the backbone nodes, like it might be, depending where you are, it might be an extra 20, 30 milliseconds away from a user. Falling back to the data centers might be an extra 50, 70 milliseconds away. So that's sort of what to expect from that.
Okay.
Hi, Jonathan Perry, MIT. So is it true that you're relying on BGP for this?
Sorry?
You're relying on BGP.
Yes.
Yeah, so, sorry. So kind of adding these maybe 3 BGP kind of routes to every router in the internet, is that expensive? And how big would a service do you think somebody would have to kind of deploy in order to use a similar technique?
So if you didn't use Anycast here, then you would likely have to have a unique IP address for every single edge location. And at that point, you've got one route, essentially, per edge location. So the number of routes we're using here is actually much smaller than what you'd get with an alternative approach.
Just that if you don't use BGP at all, you can use what your ISP's BGP lines in the routers and not have, you don't have to have a BGP kind of negotiation per IP address. You don't have to have this like /32 IP address.
Yeah, one option which we had to, if we wanted to try and keep the traffic inside of one ISP, so like say one particular ISP didn't want to serve anyone else's traffic, like a nearby ISP, then we could get them to accept a /32 IP address, and then only the users inside that particular ISP would route to that particular Anycast destination. So you can sort of hide and enforce users in one particular ISP to just go to one edge location. Don't know whether that answered your question, otherwise I can follow up afterwards if you like. Okay.
So this time all the